Welcome to the Sleepy Scientist. It's very good to have you here. Before we settle in, let me know where you're watching from tonight. Maybe you're tucked away in bed, resting under a blanket, listening from a quiet room, or letting this play softly while the world outside grows a little darker. Wherever you are, I hope you feel calm, comfortable, and ready to wander gently through a strange idea at an easy pace. If these slow scientific journeys help you relax, a like and subscribe really does help this little channel keep drifting forward. And if you're already part of this sleepy corner of the internet, thank you. Your support is deeply appreciated, even if the algorithm, being the mysterious creature it is, expresses gratitude mostly through confusing graphs. Tonight the aim is not to keep you alert with too much cosmic weirdness, although the universe may not fully cooperate. Because the more closely you look at the world around you, the more it begins to seem that you are never seeing the present exactly as it is. You're seeing light that has travelled, signals that have arrived, a version of reality that is always, in some tiny way, already gone. So let's begin, nice and slowly. Why is the world you see already in the past? The strange thing about seeing the world is that it feels instant. You open your eyes and the room appears. A hand moves and you see it move. A bird crosses the sky and there it is. A small dark shape sliding across the pale light. A lamp clicks on and the corner of the room seems to brighten at once. Vision feels immediate, as if awareness is pressed directly against reality, with no gap between what exists and what is known. But that is not quite what is happening. Every image you see arrives slightly late. Not late in the dramatic sense, not late enough for daily life to feel confusing, and certainly not late enough to justify telling someone you missed their birthday because of the finite speed of light. That would be bold, scientifically interesting perhaps, but socially risky. Still, the delay is real. The world you see is always a version of the world as it was a tiny moment ago. This happens because seeing is not a single event. It is a chain of events. Light has to travel from whatever you are looking at. That light has to enter your eye. The cells at the back of the eye have to respond. Then signals must move through the nervous system, and the brain has to turn those signals into something useful: shape, colour, movement, depth, meaning. Only after all of that does the world become the smooth, familiar experience you call seeing. So when you look at your hand, you're not receiving the hand itself. You're receiving light from the hand. More precisely, you're receiving light that has bounced off the skin, carried information about its shape and colour, passed into your eye, and begun a biological conversation inside the brain. The hand is there, of course. The delay does not make it imaginary. It simply means that your experience of it arrives by messenger. And the messenger, however fast, is never instant. The first part of this delay belongs to physics. Light travels incredibly fast, but not infinitely fast. In empty space, light moves at about 300,000 kilometers per second. That is so fast that, on the scale of an ordinary room, it might as well be immediate for almost every practical purpose. Light can cross a bedroom in a vanishingly small fraction of a second. It can travel from a lamp to your eyes so quickly that nothing about the delay is noticeable. Yet, not noticeable is not the same as not there. If a lamp across the room switches on, the light from that lamp must still cross the space between the bulb and your eyes. If someone waves from the other side of a hall, the light showing their raised hand must still travel across the air. If a bird passes overhead, sunlight reflected from its feathers must still make the journey down to you. The distances are small, so the delays are tiny. But the principle is the same one that governs moonlight, sunlight, starlight, and the faint glow of galaxies whose light began travelling long before human beings existed. That is one of the quiet beauties of physics. The same rule can be almost invisible in a room and breathtaking across the universe. The second part of the delay belongs to biology. Once light reaches the eye, seeing has still not happened. The eye is not a little window with a tiny person inside watching a cinema screen, although that would make anatomy textbooks either much easier or much stranger. Instead, the eye is a living optical instrument. The cornea and lens help focus light. The retina at the back of the eye contains specialized cells that respond to light. These cells, called photoreceptors, begin the process of turning light into electrical signals. Those signals then travel through the optic nerve toward the brain. The brain does not simply receive a finished photograph. It has to interpret patterns, compare signals, judge edges, estimate motion, and combine information from both eyes. It has to decide what belongs together, what is moving, what is near, what is far, and what might matter. Vision is not passive recording. It is active construction. This is why the world feels stable, even though the information entering the eyes is constantly shifting. Your eyes move, your head moves, objects move, light changes, shadows slide. Yet somehow, most of the time, the room remains a room, the chair remains a chair, and the cat remains a cat, even when it has chosen a deeply inconvenient place to sit. The brain is constantly organizing incoming information into a usable present, but that present is not delivered whole, it is assembled. This means there is a difference between the world as it exists and the world as it reaches awareness. The difference is usually tiny, especially nearby, but it is not meaningless. Imagine watching a hand move across a table. The actual motion happens in the world. Light from that moving hand travels to your eyes respond, your brain processes the signals. What you experience as the hand moving is therefore a carefully handled report of something that has already occurred. The same is true of a bird crossing the sky. The bird is not where you see it in the exact, absolute instant of awareness. It is where the arriving light says it was when that light began its final journey to you. Because the bird is nearby by cosmic standards, the difference is far too small to matter. But the fact remains, seeing is always receiving. Even a lamp turning on is not quite instant. The switch completes a circuit. The bulb or light-emitting diode produces light. That light spreads outward through the room. Some of it reaches your eye. Your retina responds. Your brain registers brightness. The whole process is so quick that it feels like one smooth event, but hidden inside that smoothness is a chain of cause and travel. This is not a defect in the senses. It is not the brain being unreliable. It is simply what must happen in a universe where information has to move from one place to another. No signal can reach you without crossing distance. No image can appear without light or some other form of information arriving. Even the most ordinary act of looking depends on a journey, so the present you experience is local, processed, and slightly delayed. It is not a perfect slice of the universe delivered everywhere at once. It is the result of signals that have travelled through space, entered the body, and been shaped into awareness. For nearby things, this delay is so small that life feels immediate. For the moon, it becomes more than a second. For the sun, it becomes minutes. For stars, it becomes years. For galaxies, it becomes millions or billions of years. But the idea begins here, in the quiet room, with the simplest act of looking. The world seems to arrive all at once. In truth, it reaches you piece by piece, carried by light, interpreted by the eye, gathered by the brain, and turned into the calm illusion of now. Light feels like the closest thing nature has to instant delivery. A lamp switches on, and the room brightens. A car turns a corner, and its headlights seem to reach you at once. The sun appears over the horizon, and morning arrives without any obvious pause. In ordinary life, light is so fast that it seems to ignore distance altogether, as if it simply appears wherever it is needed, politely skipping the journey. But light does not skip the journey. It travels. That single fact changes almost everything about how reality reaches an observer. If light crossed space instantly, then seeing would be much closer to a direct contact with the present. A distant star would show itself as it is now. The sun would appear as it is now. A lamp across the room would brighten the eye without even the tiniest delay. The universe would feel, in a deep physical sense, more immediately connected. Instead, light moves at a finite speed. Astonishingly fast, yes. Almost absurdly fast by everyday standards. Still finite, still limited, still obedient to the fact that travelling from one place to another takes time. In a vacuum, light travels at about 300,000 kilometers per second. That is the speed used in modern physics when people speak of the speed of light as a fundamental limit. It is so quick that light could travel around Earth several times in a single second, if it were guided neatly along the surface instead of racing through space like an overachieving courier with no interest in traffic laws. On human scales, this is why light seems immediate. A few meters across a room is almost nothing to something moving that quickly. But almost nothing is not nothing. If light takes time to cross 300,000 kilometers, it must also take time to cross 3 meters. The delay is just far too small for unaided human perception to notice. The universe has hidden the lag very well at room scale. It is there, but it is tucked away beneath the smoothness of daily experience. For a long time, it was not obvious that light had a measurable speed at all. To the human eye, light appears so immediate that many early thinkers could reasonably imagine it to be instant. Then, in 1676, the Danish astronomer Ole Rømer found evidence that light did not arrive all at once. He was studying Io, one of the large moons of Jupiter. Io regularly passes into Jupiter's shadow, creating predictable eclipses. But Rømer noticed something strange. The timing of these eclipses seemed to shift depending on whether Earth was moving closer to Jupiter or farther away from it. When Earth was farther from Jupiter, the eclipses appeared late. When Earth was closer, they appeared earlier. The moon itself was not misbehaving. Io was not looking at the timetable and deciding to add drama. The difference came from the extra distance light had to travel. When Jupiter was farther away from Earth, the light carrying the news of Io's eclipse took longer to reach observers. This was one of the great quiet turning points in science. Rømer had not measured the speed of a light with modern precision, but he had shown that light needed time to cross space. The sky itself had acted like a vast clock, and Jupiter's moon had become part of the evidence. Later scientists refined the measurement on Earth. In the 19th century, Hippolyte Fizeau used a rotating toothed wheel and a distant mirror to measure how long light took to travel out and back. It was an ingenious experiment, with a charmingly practical feeling of someone trying to catch light in the act using machinery, distance, and patience. Albert Michelson later made more precise measurements using rotating mirrors, helping turn the speed of light into one of the most important constants in physics. Over time, the speed of light became more than a large number. It became part of the structure of modern science. In James Clerk Maxwell's theory of electromagnetism, light emerged as an electromagnetic wave. In Albert Einstein's special relativity, published in 1905, the speed of light in vacuum became central to the relationship between space, time, motion, and causality. It was no longer merely the speed of something bright. It became a boundary built into the way the universe behaves. There is one important detail to keep clear. Light moves at its maximum speed in vacuum. When light travels through materials such as water, glass, or air, it moves more slowly. This slowing happens because light interacts with the material as it passes through. The effect is why a straw can appear bent in a glass of water, why lenses can focus light, and why prisms can separate white light into colours. The light is still following physical rules, but the material changes how it moves through that space. The fundamental limit, though, is the speed of light in vacuum. This is the great speed limit for information in the universe. As far as modern physics can tell, no usable signal can outrun it. A change in one place cannot inform another place instantly. Something must carry the message, and that message cannot travel faster than light in empty space. This brings the tiny delay in seeing into sharper focus. When you look across a room, the delay is almost unimaginably small, but it is made of the same principle, that makes sunlight arrive after several minutes, moonlight after just over a second, and starlight after years or centuries. The difference is not the rule. The difference is only the distance. So the world does not appear because vision touches it directly. The world appears because light has travelled from it, carrying information across space. Even at 300,000 kilometers per second, the journey still exists. And because the journey exists, the world you see has already begun to become the past. Look around the space you are in, and it probably feels completely immediate. A wall is simply there. A screen glows in front of you. A book rests on a shelf. A cup sits on a table, quietly doing the noble work of being a cup. If someone is sitting nearby, their face appears present and real, not delayed, not distant, not carried to you through time. The room seems to arrive all at once, as though seeing it is the same thing as touching the present directly. But even here, at the smallest and most familiar scale, the world is already a little old by the time it reaches you. Not old in any practical sense. The face across the table is not ancient history. The book on the shelf has not become an archaeological artifact simply because light took a fraction of a moment to reach your eyes. But the physical principle remains the same. The room around you is seen by means of travelled light, and travelled light always belongs to something that has already happened. To see an object, light must either come from it or bounce off it. A glowing screen produces its own light. A lamp produces light. A candle does the same, only with more atmosphere and slightly more commitment to fire safety. But most of the objects in a room are not shining by themselves. A chair, a blanket, a face, a notebook, a wooden floor, a glass of water, or dust drifting in a sunbeam are visible, because light has struck them and scattered into your eyes. That reflected light carries information. It carries clues about colour, brightness, texture, shadow, shape, and position. A blue cover looks blue because of how it interacts with different wavelengths of visible light. A white wall looks bright because it reflects much of the light that reaches it. A dark jumper looks dark because it absorbs more light and sends less back. Your visual world is built from these returning signals, arriving from every surface around you, and each signal has made a journey. Light may have left a bulb, crossed the room, bounced off a book, then crossed another stretch of air before entering your eye. Sunlight may have travelled from the sun, crossed space for several minutes, passed through Earth's atmosphere, slipped through a window, scattered from floating dust, and finally reached the retina. Even the quiet sparkle of dust in a sunbeam is a tiny delivery system from the past, which is a rather poetic promotion for something usually blamed for making shelves look neglected. Once light reaches the eye, it still has more work to do. It enters through the cornea, the clear curved surface at the front of the eye. The cornea begins the focusing process, bending incoming light so it can be directed properly. The light then passes through the pupil, whose size is controlled by the iris, and continues through the lens, which fine-tunes the focus. Together, the cornea and lens help form an image on the retina, the delicate light-sensitive layer at the back of the eye. The retina is where light begins to become biology. Inside the retina are specialized cells called photoreceptors. There are rods and cones, each with different roles. Rods are especially useful in dim light and help with brightness and contrast. Cones are important for colour vision and fine detail, working best in brighter conditions. These cells do not send little pictures to the brain. Instead, they respond to light by changing chemical and electrical activity, starting a chain of signals that the nervous system can use. This process is called phototransduction. It is the conversion of light into electrical signals. That word may sound like something invented by a committee trying to make vision less relaxing, but the idea is simple. The eye changes incoming light into nervous information. Without phototransduction, light could enter the eye, but the brain would have no meaningful message to interpret. The signals then begin moving from the retina toward the brain through the optic nerve. Only after that can the visual system start constructing the experience of a room, a face, a shelf, a screen, or a small, suspicious shadow that may or may not be a sock left on the floor. The brain has to interpret edges, contrast, colour, movement, distance, and meaning. Seeing is not just receiving light. Seeing is the body turning light into a world. This means the room you experience is not exactly the room at the instant of awareness. It is a reconstruction based on information that has already travelled. The delay is extraordinarily small. Across a room, light travel time is so tiny that there is no everyday need to think about it. Biological processing takes longer than the light crossing the room, but even that is usually smoothed so well by the nervous system that experience feels continuous and immediate. Still, physics does not make exceptions for cosy rooms. The finite speed of light applies whether the distance is a few meters or a few million light years. The same rule that delays the light from a distant galaxy also delays the light from a lamp beside the bed. Only the scale changes. Nearby, the delay disappears beneath ordinary perception. Far away, the delay becomes impossible to ignore. So the room is not separate from cosmic physics. It is a small, quiet example of it. The glowing screen, the face across the table, the book on the shelf, the dust in the sunlight, and the walls resting silently around you are all being delivered through travelled light. Each part of the scene arrives after crossing space, entering the eye, and being translated by the retina into signals the brain can understand. The present, then, is not handed to awareness whole and instant. It is gathered, it is carried, it is processed. Even here, before the moon, before the sun, before the stars, the world around you is already history. A tiny history, almost too brief to imagine, but real all the same. Seeing does not end at the retina. The retina is where light becomes a nervous signal, but it is not where vision becomes experience. At the back of the eye, rods and cones respond to light, and the retina begins sorting contrast, brightness, colour, and movement into patterns the nervous system can carry. But the world has not yet appeared in awareness. At this point, the brain has received the opening notes of the message, not the full song. Those signals leave the eye through the optic nerve, a bundle of nerve fibres that carries visual information toward the brain. Each eye sends information along its own optic nerve, and the pathways partially cross at a structure called the optic chiasm. This crossing helps the brain organize information from the left and right sides of the visual field. From there, much of the visual signal travels onward to the thalamus, a deep brain structure that acts as a major relay station for sensory information. One important part of the thalamus is called the lateral geniculate nucleus. It sounds rather like a Victorian railway stop for very serious neurons, but its job is genuinely important. The lateral geniculate nucleus helps relay and organize visual information before sending it to the visual cortex at the back of the brain. The visual cortex, especially the primary visual cortex, begins building the basic architecture of sight: edges, orientation, contrast, location, and motion. But even then, vision is not a simple photograph being developed inside the skull. The brain does not passively receive an image and stamp it with the label reality. It processes, compares, edits, and interprets. Different parts of the visual system specialize in different tasks. Some regions are more involved in recognizing shapes and objects. Others are more involved in tracking movement and judging where things are in space. The visual world is assembled through many interacting systems, all working quickly enough that the result feels seamless. This takes time. The delay is small, but it matters. Light may cross a room in an almost unimaginably tiny fraction of a second, yet the brain still needs additional time to turn retinal signals into a stable world. Visual processing is not one single delay that can be described perfectly for every situation, because different kinds of information are processed through different routes and at different speeds. Motion, colour, shape, depth, attention, and recognition do not all arrive in awareness in exactly the same way. The brain has to coordinate them into one useful experience. That coordination is one reason the world does not feel like a jumble of late signals. When you watch a ball move through the air, the brain is not merely recording each position after it happens, it is also estimating where the ball is going. When you walk across a room, the brain combines vision with signals from the inner ear, muscles, joints, and skin to help maintain balance. When you read someone's face, the brain uses tiny changes in expression, memory of familiar patterns, and attention to judge emotion. The present you experience is not raw information, it is organized information. A major idea in neuroscience called predictive processing helps describe part of this. Predictive processing suggests that the brain is constantly using expectations to interpret incoming sensory data. It does not mean the brain is making everything up. The outside world is very much involved. A chair remains a chair even if the brain occasionally disagrees with the location of your keys. But the brain is not waiting passively for perfect information. It is comparing what it expects with what the senses deliver, then updating its model of the world. This is useful because sensory information is always arriving after a journey. Light has travelled. The retina has responded. Signals have moved through the optic nerve and thalamus. Processing has unfolded across the visual cortex and related brain regions. If the brain simply waited for everything to arrive in full before acting, life would become clumsy and slow. Catching a falling object, stepping off a curb, avoiding a low branch, or noticing a moving car will require the brain to handle late information quickly and intelligently. So the brain smooths the world. It fills in continuity between moments. It stabilizes the visual scene despite constant eye movements. It helps moving objects appear fluid rather than as a series of broken positions. It merges information from both eyes into depth. It adjusts to changing light so a white page still looks white in morning sun, cloudy daylight, or under a warm lamp. It gives you a usable world, not because the information is perfectly instant, but because the nervous system is remarkably good at working with delay. This also explains why awareness can feel immediate even when it is not. The brain is not presenting you with a timestamp saying, "This visual scene was assembled slightly after the fact, please enjoy responsibly." It simply gives you the best working present it can. For almost every ordinary purpose, that is enough. You can reach for a glass, recognize a friend, read a sentence, walk through a doorway, and judge where the floor is, which is always a welcome feature in any room. The important point is that the past is not only carried by light through space, it is also shaped by the nervous system before it becomes experience. The light from a face, a book, a screen, or a drifting speck of dust has already taken time to arrive. Then the body adds its own quiet delay, converting light into signals, sending them through neural pathways, and assembling them into a world that feels present. The present, as the brain gives it to you, is not a raw slice of reality. It is a living construction made from late information, carefully organized so well that you hardly notice the delay at all. Sound makes delay easier to notice because sound is much slower than light. Light is so fast that ordinary distances usually hide its travel time from human experience. A lamp turns on, and brightness seems to appear instantly. A person waves from across a street, and the movement seems to arrive in the eye without any obvious pause. But sound is different. Sound moves slowly enough that the gap between an event and our awareness of it can become part of daily life. It is one of the clearest ways nature reveals that the present does not reach the senses all at once. The classic example is lightning and thunder. A lightning flash and the crash of thunder come from the same event. A sudden electrical discharge heats the air around it extremely quickly, causing the air to expand violently and produce a powerful pressure wave. That pressure wave travels outward as sound, but the light from the lightning crosses the distance to your eyes far faster than the sound reaches your ears. So the sky flashes first, and the thunder follows afterward, rolling in from the same moment but arriving late. In air at ordinary temperatures, sound travels at roughly 340 meters per second. The exact speed changes with temperature, humidity, and pressure, because sound is a vibration passing through matter, and matter is never quite the same everywhere. Warmer air usually lets sound travel a little faster than colder air. Still, the rough figure is enough to make the difference clear. Light can cross hundreds of thousands of kilometers in a second. Sound in air covers only a few hundred meters in the same time. It is not slow in the everyday sense, but beside light it looks like it stopped to admire the scenery. This is why counting the seconds between lightning and thunder can give a rough sense of how far away a storm is. The flash reaches you almost immediately on local scales, but the sound takes noticeably longer. If several seconds pass before the thunder arrives, the lightning happened some distance away. The event was already over, but the sound was still travelling toward you, carrying its delayed announcement through the air. Fireworks show the same effect in a gentler way. You may see the bright burst open in the sky, spreading colour above a park or distant field, and only afterward hear the soft boom. The light arrives first, delicate and immediate looking. The sound follows, rounder and slower, as though the sky is remembering what just happened. At a large stadium, a crowd on the far side may rise, cheer or clap, and there can be a tiny delay before the noise reaches the other end. The event is visible before it is audible. The same thing can happen with ordinary objects at a distance. Imagine seeing an axe strike a log far across a field. The movement appears first. The arm rises, the blade falls, the wood splits. Then, a moment later, the sharp sound reaches you. The sight and the sound belong to the same action, yet they arrive separately. Your brain has to make sense of them as one event, even though they have travelled through the world at very different speeds. Echoes are another quiet lesson in delay. When sound waves strike a hard surface, such as a cliff face, a large wall, or the inside of a tunnel, some of the sound reflects back. The echo is not a copy made by magic. It is the same kind of pressure wave returning after a longer journey. The delay between the original sound and the echo tells you that the sound has travelled outward, struck a surface, and come back. The space has briefly revealed its size through time. This does not mean sound replaces the deeper story of light. The title is still mostly about seeing, and vision depends on light that has crossed space before reaching the eyes. But sound helps the idea become emotionally obvious. It lets delay step out of abstraction. You do not have to imagine galaxies or equations. You can hear the gap in thunder, fireworks, echoes, footsteps in a hall, or a distant door closing after you have already seen it move. The senses do not receive reality in perfect synchrony. Vision, hearing, touch, balance, and body awareness all depend on different signals, different pathways, and different speeds. Light reaches the eye quickly. Sound reaches the ear more slowly. Touch depends on mechanical contact and nerve signals moving through the body. The brain then has to combine these arrivals into one working experience of the world. It performs this coordination so smoothly that most of the time everything feels unified. That unity is a construction, a useful one, a reliable one, and usually an extremely convincing one. But it is still built from signals arriving after different journeys. The brain does not receive a finished present. It gathers delayed messages and binds them together into the feeling of now. Sound simply makes the delay easier to catch in the act. It reminds you that events do not arrive whole. They send out messengers. Some are fast, some are slower, and all of them take time to reach you. The world does not step directly into awareness. It travels there. A mirror feels like a little window into the present. You stand in front of it, and there you are. A face, a room behind you, a light on the ceiling, a doorway, a shadow, perhaps the faint evidence of hair that has made its own independent decisions overnight. It all seems immediate. The mirror appears to show reality at the exact moment you look. But a mirror is not showing you the present directly. It is returning light. The image in a mirror is not a separate object living behind the glass. There is no second room tucked away inside the wall, no reverse world where everything is slightly more organized and left hands become right hands. A mirror image is created because light follows a path. Light leaves an object, reaches the mirror, reflects from its surface, and then travels into your eyes. What you see is the result of that journey. This means a mirror adds another step to the delay. If you look at your face in a bathroom mirror, light from the room strikes your face, scatters from your skin, travels to the mirror, reflects from the mirror's surface, and then comes back into your eyes. From there, the eye and brain still have to do their own work, focusing the light, converting it in the retina, sending signals through the optic nerve, and building the visual experience. For a mirror close to you, this delay is unbelievably small. Light is so fast that the extra journey makes no practical difference in daily life. The version of yourself in the mirror seems perfectly current. But physics is very strict about travel. Even reflected light must take the long way round, however short that long way happens to be. The behavior of mirrors is described by the law of reflection. In simple terms, light reflects from a smooth surface at the same angle at which it arrives. This is why a flat mirror gives a clear image. Its surface is smooth enough that light rays keep an orderly relationship after bouncing away. A rough surface scatters light in many directions, so it does not form the same sharp reflection. That is why a polished mirror can show a face clearly, while a painted wall mostly shows only colour and brightness. Reflection is one of the basic processes that shapes the visible world. Absorption is another. When light strikes a material, some wavelengths may be absorbed, meaning their energy is taken into the material rather than sent back toward the eye. Scattering is also important, because light can be redirected in many directions after interacting with tiny particles, rough surfaces, or uneven structures. Together, reflection, absorption, and scattering decide whether something looks shiny, dull, bright, dark, smooth, cloudy, transparent, or coloured. A bathroom mirror is simply a very controlled example of reflection. Still water can do something similar on a calm day. A lake may hold the shape of a mountain, a tree, or the moon, not because those things have duplicated themselves in the water, but because light has bounced from them to the water's surface, and then onward to the observer. When the water ripples, the reflected image breaks apart, because the surface angles change and the light no longer returns in the same neat pattern. Polished metal also reflects light, though often less perfectly than a mirror. A spoon can bend a face into a strange curved version of itself, which is helpful if you ever need a reminder that optics has a sense of humour. The curved surface sends light back in changing directions, stretching and compressing the image. The object has not changed. The path of the light has. Glass windows at night create another familiar kind of reflection. When a room is brightly lit and the outside is dark, the window can act like a weak mirror. You may see both the darkness beyond the glass and the ghostly reflection of the room behind you. The window is transmitting some light, reflecting some light, and quietly turning an ordinary pane of glass into a small physics demonstration. Moonlight reflected from the ocean works on a much larger and calmer scale. The moon itself shines because it reflects sunlight. When that moonlight reaches the sea, the moving surface scatters and reflects it again, sending silver paths across the water toward the eyes of an observer on shore. That glow has travelled from the sun, bounced from the moon, touched the restless surface of Earth's ocean, and then arrived as a soft line of light. It feels peaceful, but its journey is wonderfully complicated. Mirrors and reflections remind us that seeing is not direct possession of the present. It is the reception of light after a path through space. Sometimes that path is simple, sometimes it bounces, sometimes it scatters from water, metal, glass, skin, clouds, or dust. But it always takes time. Sound may delay obvious because it travels slowly enough for the gap to be heard. Light hides the gap better, especially nearby, but it does not remove it. Even the clearest mirror shows a returned past. Not an ancient past, not a dramatic past, but a past all the same. Every reflection is a little echo made of light. The moon is far enough away for light delay to stop being merely a hidden idea and start becoming something you can almost feel. When you look across a room, light reaches your eyes after such a tiny fraction of a second that the delay disappears beneath ordinary experience. When you look into a mirror, the light has made a slightly longer journey, bouncing from object to glass and back again, but it still feels instant. The delay is real, yet much too small to notice. The moon changes the scale. On average, the moon is about 384,000 kilometers from Earth. That distance is not fixed, because the moon's orbit is slightly elliptical rather than perfectly circular, so sometimes it is closer and sometimes farther away. But the average is enough to make the point. Light from the moon takes just over 1 second to reach Earth, so when you look up at the moon, you do not see it exactly as it is in that instant. You see it as it was a little more than 1 second ago. That may not sound like much. 1 second is hardly ancient history. It is not enough time to become nostalgic unless you are extremely committed to memory. But it is a real separation between the moon itself and the moon as it appears. The moon in the sky is not a live broadcast with no delay. It is a slightly delayed arrival, a bright message that has crossed hundreds of thousands of kilometers before entering the eye. There is another beautiful detail hiding inside that moonlight. The moon is not glowing by itself. It is not a small star. It does not produce its own visible light in the way the sun does. The moon shines because it reflects sunlight. Light leaves the sun, travels to the moon, strikes its dusty surface, scatters from lunar rock and regolith, and then some of that reflected light travels onward to Earth. So moonlight is already a traveller before it reaches the moon, and then it travels again before reaching you. Sunlight takes several minutes to cross the distance from the sun to Earth's neighbourhood. Some of it hits the moon. Then the moon sends a small fraction of that light across the Earth-Moon distance, adding just over a second to the journey. By the time moonlight enters your eyes, it has already followed a long and delicate path through space. In that sense, the moon is like an enormous natural mirror, though not a neat polished one. Its surface is rough, dusty, cratered, and uneven. It reflects sunlight in many directions rather than giving the kind of sharp reflection seen in a bathroom mirror. The correct term for much of this behaviour is scattering. Sunlight strikes the lunar surface and is redirected from countless grains of dust, rocks, crater walls, and ancient volcanic plains. This scattered light is what allows the moon to glow softly in the night sky. The moon's brightness is also shaped by its phase. A full moon appears bright because the side facing Earth is also strongly lit by the sun. A crescent moon appears slimmer because only a portion of the sunlit half is visible from Earth. Nothing mysterious has been carved away from the moon. It is still round, still there, still quietly orbiting. The changing shape is geometry. Sun, moon, and Earth shifting their angles around one another. The fact that light takes time to travel is not only a poetic thought, it is also something scientists use for measurement. During the Apollo program, astronauts place special reflectors on the lunar surface. These devices are called retroreflectors. They are designed to send incoming light back toward its source. Scientists on Earth can aim powerful laser pulses at these retroreflectors, wait for the reflected light to return, and measure the round-trip travel time. This method is called lunar laser ranging. It is one of the most precise ways of measuring the distance between Earth and the Moon. Because light travels at a known speed, the timing of the laser's journey can be used to calculate distance with remarkable accuracy. NASA, the Apollo missions, and later scientific observatories all became part of this quiet experiment in cosmic measuring. A beam of light goes out, touches a device left by human hands on another world, and comes back with a number. Lunar laser ranging has also helped confirm that the Moon is slowly moving away from Earth by a few centimeters per year. That gradual drift is connected to tidal interactions between Earth and the Moon. It is not a dramatic escape. The Moon is not packing a suitcase. But over long spans of time, the Earth-Moon system is changing, and light travel time helps reveal that change. This makes the Moon a perfect bridge between ordinary vision and cosmic distance. It is close enough to feel familiar, close enough to shape tides, calendars, myths, night skies, and human exploration. Yet it is far enough away that seeing it means receiving the past in a way that can be named and measured. The mirror in a room returns light from a tiny fraction of a moment ago. The Moon returns sunlight from a little more than 1 second ago. The same principle has simply become larger, clearer, and more beautiful. When you look at the Moon, you're seeing a world that has already moved slightly onward. Its light left before your eyes received it. Its image crossed the darkness first. And in that small delay, the familiar Moon becomes something quietly astonishing, the nearest great reminder that vision is always a message from the past. The sun feels immediate because daylight is everywhere before you have time to think about it. Morning brightens the sky, shadows stretch across the ground, windows glow, leaves turn golden, and the world seems to receive the sun all at once. It feels like direct contact with the star at the centre of the solar system, as though sunlight is a thread tying Earth to the present moment of the sun itself. But the sun you see is not the sun as it is right now. Sunlight takes roughly 8 minutes and 20 seconds to travel from the sun to Earth. That means the bright disk in the sky is an image from the recent past. The sun could never appear to you in perfect real time, because its light has to cross the enormous distance between the star and this planet before it can enter the atmosphere, scatter through the sky, reflect from the world around you, and finally reach your eyes. The average distance from Earth to the sun is about 150 million kilometers. Astronomers call this distance an astronomical unit. It is one of the most useful measuring sticks in the solar system because it gives a simple reference for the distances between the sun, planets, asteroids, and spacecraft. 1 astronomical unit is the distance sunlight must cross before it becomes daylight here. And even for light, that journey takes time. This is a larger version of the same idea revealed by the Moon. Moonlight takes just over 1 second to reach Earth after reflecting from the lunar surface. Sunlight stretches the delay into minutes. The gap is still short enough that everyday life feels perfectly connected to the sun, but long enough to be deeply strange when you pause with it. The warmth on your face, the brightness on the wall, the sunlight on a tree outside the window, all of it began its final journey from the sun more than 8 minutes before you received it. This has an important consequence. If the sun could suddenly change, Earth would not know immediately. The light from that change would take roughly 8 minutes and 20 seconds to arrive. Even changes in gravity would not be felt instantly, because in modern physics, gravitational changes also propagate at the speed of light. The universe does not allow distant information to update everywhere at once. A change must travel. A message must cross space. This does not mean the sun is about to perform any sudden dramatic tricks. Stars are not usually in the habit of vanishing without warning, which is considerate of them. The point is not danger. The point is connection. Earth is tied to the sun by light, gravity, energy, and motion. But those connections are not instantaneous. They are carried across space at a finite speed. The sunlight itself begins with nuclear fusion in the sun's core. Deep inside the sun, under immense pressure and temperature, hydrogen nuclei combine through a chain of reactions that ultimately forms helium and releases energy. This process is called nuclear fusion. It is the reason the sun shines, the reason Earth receives warmth, and the reason almost every sunny afternoon is secretly powered by physics taking place in a dense sphere of plasma about 150 million kilometers away. The sun is made mostly of plasma, a state of matter in which atoms are stripped into charged particles. In the core, fusion releases energy in the form of radiation and motion among particles. But the energy created deep inside the Sun does not simply fly straight out into space. Before sunlight can leave the Sun's visible surface, that energy may spend a very long time moving outward through the solar interior. Photons are absorbed, re-emitted, scattered, and redirected many times as they work through the dense inner layers. The exact journey is complex, and it is better to think of it as energy, gradually diffusing outward rather than a single little photon politely walking from the core to the surface with a packed lunch. Estimates vary, but the energy that eventually emerges as sunlight may take thousands of years, or much longer, to escape from the Sun's interior. Then, once it reaches the photosphere, the visible surface of the Sun, the final trip to Earth takes only about 8 minutes and 20 seconds. The photosphere is the layer from which most visible sunlight escapes into space. It is not a solid surface like the ground beneath your feet. It is a glowing layer of hot plasma with granules, magnetic activity, sunspots, and constant motion. Organizations such as NASA and the European Space Agency study the Sun using spacecraft and observatories designed to watch its light, magnetic fields, charge particles, and eruptions. Missions such as the Solar Dynamics Observatory and Solar Orbiter help scientists understand how the Sun behaves, how it changes, and how its activity affects space weather around Earth. Yet even the most advanced solar telescope receives old information. Every image of the Sun taken from near Earth shows the Sun as it was minutes ago. Every solar flare observed from Earth has already happened by the time its light arrives. Every patch of sunlight on the floor is a finished journey. So the delay has grown. The room around you is only a tiny fraction of a moment old. The moon is just over 1 second old. The Sun is more than 8 minutes old. And with that, the visible present begins to stretch. What once seemed immediate becomes a chain of arrivals, each shaped by distance. The Sun still feels present because life on Earth has always lived inside this delay. But physics quietly reminds us that daylight is not the Sun reaching out instantly. It is the Sun arriving late, beautifully, and right on time. The planets do not all arrive to us from the same depth of time. From Earth, the solar system can feel like a neat arrangement of neighbouring worlds, all sharing the same broad present. Mercury circles close to the Sun. Venus shines brightly before sunrise or after sunset. Mars glows red in the night sky. Jupiter and Saturn look calm and steady, like distant lanterns hung in the dark. They all seem to belong to now, but each one is seen after a different delay. The reason is simple. The planets are always moving. Earth is moving around the Sun, and so are the other planets. Sometimes Earth and another planet are relatively close together on the same side of the Sun. At other times, they are separated by enormous distances, with the Sun somewhere between them or with their orbits carrying them far apart. Because light and radio signals travel at a finite speed, the delay depends on the changing distance. The planets are not seen from one fixed time in the past. They are seen through a constantly changing light travel time. Mars is one of the clearest examples. It is close enough to feel like a neighbour by planetary standards, but far enough away for the delay to matter. When Earth and Mars are near each other in their orbits, light can take only a few minutes to travel between them. When they are much farther apart, the delay can stretch beyond 20 minutes. So Mars in a telescope is not Mars in perfect real time. It is Mars as it was when the reflected sunlight left its surface and began crossing the space between the two planets. This does not mean Mars is a frozen relic. It is not locked in some ancient version of itself. It has weather, dust, polar caps, thin clouds, winds, seasonal changes, and an atmosphere made mostly of carbon dioxide. It is a real world continuing to change. But whatever information reaches Earth from Mars is information that has travelled. By the time a signal arrives, the planet has already moved onward. The same is true for spacecraft near Mars. When NASA sends commands to a rover, the message does not arrive instantly. It travels as a radio signal at the speed of light, crossing millions of kilometers before it reaches the spacecraft or the rover on the surface. The rover's response then has to make the journey back. Depending on the positions of Earth and Mars, the round-trip delay can be long enough that direct real-time driving is impossible. That is why a Mars rover cannot be controlled like a remote control car in a park. There is no joystick in a control room making it turn left at the exact moment a person moves their hand. By the time a command reaches Mars, the situation there is already minutes old. By the time the rover sends back images or data, those too are delayed. If the rover encounters a rock, a slope, or a patch of soft soil, engineers on Earth learn about it only after the information has crossed space. This is where mission planning becomes essential. NASA's Mars rovers, including Spirit, Opportunity, Curiosity and Perseverance, have been operated with careful planning rather than instant control. Engineers and scientists at the Jet Propulsion Laboratory, often shortened to JPL, study images, plan routes, choose targets, build command sequences, and send instructions for the rover to carry out. The rover also has onboard systems that help it avoid hazards and manage tasks without needing someone on Earth to react instantly to every pebble, which is wise because Mars has rather a lot of pebbles and very poor customer service. This delay turns space exploration into a conversation with pauses. Earth speaks, then waits. Mars replies, then Earth waits again. The silence between messages is not emptiness. It is distance made audible through time. Other planets bring their own delays. Venus can be relatively nearby compared with the outer planets, but its thick atmosphere hides the surface from ordinary visible light, so radar and spacecraft observations become especially important. Jupiter is much farther away, so its light and radio signals take tens of minutes to reach Earth, depending on where both planets are. Saturn is farther still. Uranus and Neptune are so distant that signals can take hours to cross the gap. In each case, the planet seen through a telescope is not presented instantly. It is delivered by light. Spacecraft data is not received instantly either. It is delivered by radio waves, which are part of the electromagnetic spectrum and travel through vacuum at the same fundamental speed as light. Whether the message is visible, light reflected from a cloud top, infrared radiation from a warm atmosphere, or a radio transmission from a probe, it still has to cross space. This is a practical fact, not just a poetic one. Planetary science depends on understanding observation time, signal travel, orbital motion, and geometry. A spacecraft photograph of Jupiter, a radar map of Venus, a rover image from Mars, or data from a probe near Saturn, all represent a world as measured after the signal has travelled. The delay must be accounted for, especially when navigating spacecraft, landing on another planet, or timing observations of moons, rings, atmospheres, and storms. The Sun showed that the nearest star reaches Earth after about 8 minutes. The planets show that delay is not a single fixed number across the solar system. It stretches and shrinks as worlds move. Distance changes. Orbits carry planets closer and farther away. The visible and measurable present of each world arrives on its own schedule. So the solar system is not one perfectly synchronized room. It is a moving family of delayed messages. Every planet shines from a slightly different past, and every signal carries a quiet reminder that even nearby worlds must be reached across time. The planets are close enough that their delays can still be counted in minutes or hours. But stars are different. Stars carry the idea into a much larger and quieter kind of time. Once you move beyond the solar system, distance becomes so vast that seconds and minutes no longer feel useful. The numbers grow too large, too quickly. Astronomers stop asking how many minutes light has travelled and begin speaking in years. This is where the light year enters the story. A light year is the distance light travels in 1 year. It sounds as if it should be a measurement of time, because the word year is right there, quietly causing trouble. But a light year is not a length of time, It is a distance. It is the stretch of space crossed by light in one full year, moving through vacuum at about 300,000 kilometers per second. Over a year, that becomes an enormous distance, roughly 9.5 trillion kilometers. So when a star is described as being 4 light years away, it means the light from that star takes about 4 years to reach us. When you see it tonight, you see it as it was 4 years ago. The star may still be shining now, but the version arriving in your eyes began its journey years earlier. The nearest known star system to the Sun is Alpha Centauri, and within that system the closest individual star to us is Proxima Centauri. Its light takes a little over 4 years to reach Earth. That makes Proxima Centauri our nearest stellar neighbour, yet even this closest star has seen years in the past. It is nearby only by the very generous standards of astronomy, where next door can still mean light travelling for more than 4 years before it arrives. Sirius, the brightest star in the night sky as seen from Earth, is farther away. Its light takes a little over 8 years to reach us. When Sirius shines above the horizon, you're seeing light that left before many recent memories had even happened. The star looks fresh and sharp in the sky, but its brightness is a message from years ago, arriving quietly across interstellar space. And those are close stars. Many familiar stars are much farther away. Some of the bright stars in well-known constellations are seen as they were decades ago. Others are seen centuries in the past. Some stars visible to the unaided eye are thousands of light years away, meaning their light began travelling when human history looked very different. A star may appear to sparkle in the night sky with the freshness of the present, but what reaches the eye is an old signal, not a live performance. The stars are not ancient because they are dead or still. Many are actively shining, burning through nuclear fusion, changing slowly over time, producing winds, magnetic activity, and sometimes immense eruptions. But the information we receive from them is old because it has had to cross the space between their surfaces and our eyes. A star can be very alive and still be seen through ancient light. Measuring these distances was one of the great challenges in astronomy. For centuries the stars looked fixed against the sky, and their distances were difficult to grasp. One key method is called stellar parallax. The idea is beautifully simple. As Earth moves around the Sun, nearby stars appear to shift very slightly against the background of more distant stars. The shift is tiny, because even nearby stars are so far away. But if it can be measured, it reveals distance. The effect is similar to holding a finger in front of your face and looking at it first with one eye, then the other. Your finger appears to move against the background, not because the finger has actually jumped sideways, but because your viewpoint has changed. Earth's orbit provides astronomy with a much larger version of that shifting viewpoint. The farther away a star is, the smaller its apparent shift becomes. In the 19th century, the German astronomer Friedrich Bessel made one of the first successful measurements of stellar parallax. In 1838, he measured the distance to the star 61 Cygni, showing that the stars were not merely lights painted on a nearby celestial sphere, but objects scattered across immense depths of space. It was a quiet but enormous step. The sky gained distance, the stars gained scale. The night became deeper than human imagination had comfortably allowed. Today, stellar distances are measured with extraordinary precision by missions such as the European Space Agency's Gaia spacecraft. Gaia has mapped the positions and motions of more than 1 billion stars in the Milky Way, measuring tiny changes with astonishing accuracy. It has turned the galaxy into a moving 3-dimensional map, helping astronomers understand not only where stars are, but how they travel through space. All of this deepens the central idea. The planets showed that light delay changes as worlds move around the Sun. Stars turn that same principle into a natural time machine, not a machine of metal and gears, not a doorway to step through, but a simple consequence of distance and light. Looking outward becomes looking backward. Every star is a message. Some messages are only a few years old, Some began travelling before modern cities, before telescopes, before written history. They cross the dark patiently at the fastest speed the universe allows, and still they arrive late. The night sky is not a picture of the universe all at once. It is a sky full of different pasts shining together. A telescope is often described as an instrument for seeing farther away. That is true, but it is only half the magic. A telescope does not simply bring distant objects closer, as if the universe has agreed to lean politely toward the lens. A telescope collects light. And when that light has crossed enormous distances, collecting it means receiving something old. The farther away the source, the longer the light has been travelling. So a telescope is not only a tool for seeing across space, it is also a tool for looking back in time. This is one of the most beautiful ideas in astronomy. A telescope does not need to break the laws of physics to become a time machine. It only needs to gather light that has already spent years, centuries, millions of years, or billions of years on its way. Every faint point, every smudge of a galaxy, every distant glow is a message from an earlier version of the universe. The basic job of a telescope is to collect more light than the human eye can gather alone. The pupil of the eye is small, so it can only receive a limited amount of light. A telescope uses a larger lens or mirror to collect far more. The larger the collecting surface, the more light it can gather, and the fainter the objects it can reveal. This is why large telescopes can show stars too dim for unaided vision, nebulae too faint to notice, and galaxies so remote that their light began travelling long before humans existed. In 1610, Galileo Galilei turned a telescope toward the sky and changed humanity's view of the cosmos. He observed mountains and craters on the moon, many more stars than the eye could see alone, the phases of Venus, and 4 bright moons orbiting Jupiter. Those observations helped weaken the old idea that everything in the heavens must circle Earth, and they supported the growing case for the sun-centered model associated with Nicholas Copernicus. Galileo's telescope was modest by modern standards, but it opened a door. Modern telescopes are far more powerful and technically complex. They use enormous mirrors, sensitive detectors, precise computers, adaptive optics, cooling systems, and spacecraft engineering. Some observe visible light. Others study infrared light, radio waves, ultraviolet light, X-rays, or gamma rays. Together, they allow astronomers to see the universe in many different forms of light, not just the narrow range visible to human eyes. The Hubble Space Telescope is one of the most famous examples. Launched by NASA and the European Space Agency in 1990, Hubble orbits above most of Earth's atmosphere, giving it a clearer view of space than ground-based telescopes usually have. It has observed stars, nebulae, galaxies, supernovae, black holes, and some of the deepest fields ever imaged. When Hubble looks at a galaxy millions or billions of light-years away, it is not seeing that galaxy as it is today. It is seeing the galaxy as it was when its light began the journey. The James Webb Space Telescope extends this idea even further. Built by NASA, the European Space Agency, and the Canadian Space Agency, Webb observes mainly in infrared light. This is especially important for distant galaxies because the expansion of the universe stretches their light toward longer wavelengths. Visible light from very distant early galaxies can be stretched into infrared before it reaches us. Webb is designed to detect that stretched ancient light, allowing astronomers to study galaxies from the early history of the universe. This stretching of light is called redshift. In simple terms, as the universe expands, the space between distant galaxies and us expands too. Light travelling through that expanding space gets stretched. Its wavelength becomes longer, and longer wavelengths tend toward the redder or infrared side of the spectrum. The greater the redshift, generally, the longer the light has travelled, and the farther back in cosmic history astronomers are looking. Edwin Hubble played a central role in showing that distant galaxies are moving away from us in a pattern linked to distance. Georges Lemaitre, a Belgian priest and physicist, had already developed the idea of an expanding universe from general relativity. Together, their work helped form the foundation of modern cosmology. The universe was not understood as static and eternal in the old simple sense, but as expanding and changing over time. This means telescopes reveal not only distant places but different ages. A nearby star may be seen a few years in the past. A galaxy in the local universe may be seen millions of years ago. A very distant galaxy may be seen as it was when the universe was young, still building many of its first large structures. Astronomy becomes a kind of layered history, where distance and time are woven together by the finite speed of light. The strange part is that all these ages appear in the same sky. One star may show light from a decade ago. Another may show light from centuries ago. A galaxy may show light from before complex life existed on Earth. A deeper galaxy may show a universe that had not yet formed the familiar shapes seen nearby today. The night sky is not a single photograph of one universal moment. It is a mosaic of arrivals. The stars already showed that light can travel for years before reaching Earth. Telescopes carry that same idea beyond the nearby Milky Way. They gather faint old light, concentrate it, measure it, and let scientists read the history written inside it. To look outward, once the distances become large enough, is to look backward. A telescope does not make the universe immediate. It reveals how patiently the past has been travelling toward us. A galaxy is not just a distant object. From Earth, it is also a fossil made of light. When you look at a nearby object, the delay is almost impossible to notice. When you look at the Moon, the delay becomes just over 1 second. When you look at the Sun, it becomes about 8 minutes and 20 seconds. Stars stretch that delay into years, decades, centuries, or longer. But galaxies carry the idea into truly deep time, because many of them are so far away that their light began travelling before human beings existed, before mammals existed, and in some cases before Earth itself had settled into the world we know. A distant galaxy does not appear as it is now. It appears as it was when its light began crossing the universe. That light has travelled through expanding space, passing through vast dark regions between galaxy clusters, before finally reaching telescopes near Earth. The galaxy may have changed enormously since the light left. Stars may have formed, others may have died, clouds of gas may have collapsed, spiral arms may have shifted, galaxies may have merged, disturbed one another, or grown quieter with age. But the light arriving now belongs to an earlier chapter of that galaxy's life. The Andromeda Galaxy is a good place to begin, because it is close by galactic standards and visible to the unaided eye under dark skies. Andromeda is roughly 2.5 million light-years away. That means the light reaching Earth tonight left Andromeda about 2.5 million years ago. When that light began travelling, early humans had not built cities, written books, launched spacecraft, or made unnecessarily complicated coffee orders. The Earth was a different world. Yet the light continued patiently across intergalactic space, and only now does it enter human eyes and instruments. Andromeda is nearby in the language of galaxies. That is the slightly dizzying part. It is our neighbouring large galaxy, a member of the local group, and it is still seen millions of years in the past. Once telescopes look beyond the local group, the delays grow far larger. Galaxies and distant clusters may be seen as they were hundreds of millions or billions of years ago. Some of the most distant galaxies observed by modern telescopes are seen from a time when the universe was young, before it had built the mature galaxy populations visible closer to us today. This gives astronomy a remarkable advantage. Since light takes time to travel, astronomers can compare galaxies at different distances and, in a sense, compare galaxies at different ages. Nearby galaxies show the universe more recently. Farther galaxies show earlier periods of cosmic history. Very distant galaxies reveal the universe when it was still young and busy, full of intense star formation and smaller structures still growing into larger ones. This is how scientists study galaxy evolution. Galaxies are not all the same. Some are spiral galaxies, like the Milky Way, with flattened disks, spiral arms, gas, dust, and ongoing star formation. Some are elliptical galaxies, often older and smoother in appearance, with less cold gas available for making new stars. Some are irregular galaxies, shaped by interactions, collisions, or internal turbulence. Young star-forming galaxies can glow strongly with hot blue stars, while older galaxies may shine more gently with redder, longer-lived stars. Each type holds clues about how matter gathered, cooled, formed stars, and changed over cosmic time. Deep field images made this idea especially powerful. The Hubble Deep Field, created from observations by the Hubble Space Telescope in the 1990s, focused on a tiny patch of apparently empty sky. Instead of emptiness, it revealed thousands of galaxies, many incredibly faint and distant. The Hubble Ultra Deep Field went even deeper, showing galaxies from much earlier cosmic times. These images changed the emotional scale of the sky. A dark, blank patch was not truly empty. It was crowded with ancient light, waiting for an instrument patient enough to collect it. The James Webb Space Telescope has extended this view further, especially through infrared observations. Because the universe is expanding, light from very distant galaxies is stretched as it travels. This stretching is called redshift. Light that began as ultraviolet or visible radiation can arrive shifted into infrared wavelengths. Webb was designed to see that kind of ancient stretched light, allowing astronomers to study early galaxies in more detail than before. It reveals young galaxies forming stars, assembling structure, and helping scientists understand how the first generations of galaxies grew after the early universe became transparent. So telescopes do not simply reveal more objects. They reveal time stacked across the sky. One galaxy may show the universe as it was a few million years ago. Another may show it billions of years ago. A faint red smudge in a deep image may be light from a young galaxy, whose modern form, if it still exists, is far beyond what can be seen directly from Earth today. That is why galaxies can be thought of as fossils made of light. They are not fossils because they are dead, and they are not frozen in place. They are fossils because their arriving light preserves an earlier state. The universe has allowed its past to remain visible, not by keeping it nearby, but by letting its light travel for a very long time. When telescopes look deeply into space, they gather those delayed messages. They do not show one universal present. They show many moments at once, layered by distance, stretched by expansion, and carried across the dark with extraordinary patience. There is a point where looking back in time reaches a kind of glowing wall. Not a solid wall, not an edge of space, not a barrier floating somewhere out beyond the galaxies like the universe decided to install a curtain. It is a limit in what light can show us directly. Beyond the ancient galaxies seen by powerful telescopes, beyond the faint red smudges whose light has travelled for billions of years, there is an even older signal spread across the whole sky. It is called the cosmic microwave background. The cosmic microwave background is the oldest light directly observed across the universe. It arrives from a time when the universe was very young, only about 380,000 years old. That is young by cosmic standards, though still old enough to make a human birthday cake rather impractical. Today, this light is not visible to human eyes. It has been stretched by the expansion of the universe until it now reaches us mostly as microwave radiation, a faint, cool glow coming from every direction in space. This ancient light began its journey when the universe changed from being opaque to being transparent. Before that time, the universe was hot, dense, and filled with charged particles. Electrons moved freely among atomic nuclei, and light could not travel very far without being scattered again and again. The early universe was not dark in the simple sense. It was filled with radiation. But it was foggy to light because photons could not move across large distances in straight paths. Then the universe expanded and cooled. Eventually, electrons and protons could combine to form neutral hydrogen atoms. This process is often called recombination, although the name is slightly misleading because the electrons and protons were combining in this way for the first time. Once neutral atoms formed, light could travel much more freely. The cosmic fog lifted. Photons that had been trapped by constant scattering were suddenly able to move through space. That released light is what we now observe as the cosmic microwave background. It is important to be precise here. The cosmic microwave background is not light from the Big Bang itself. The earliest moments of the universe were far too hot and dense for light to travel freely in the way it does now. Instead, this background is light from the hot early universe after it became transparent. It is a kind of afterglow, not from the first instant, but from the moment the universe became clear enough for light to cross it. When that light began travelling, there were no stars yet, no galaxies, no planets, no Earth, no oceans, forests, eyes, telescopes or people, wondering why everything is quite so large and emotionally inconvenient. The universe was mostly a hot, nearly uniform mixture of hydrogen, helium, dark matter, radiation, and tiny variations in density. Those tiny variations mattered enormously. They were the slight unevenness from which later structure could grow. Over billions of years, gravity amplified those small differences. Slightly denser regions attracted more matter. Gas collected. Dark matter helped shape large cosmic structures. Eventually the first stars formed, then galaxies, then clusters and filaments, then the vast web of structure seen in the modern universe. The cosmic microwave background gives scientists a map of the early conditions from which all that later complexity emerged. The discovery of this background was one of the great confirmations of the Big Bang model. In 1965, Arno Penzias and Robert Wilson detected a persistent microwave signal while working with a radio antenna at Bell Labs. At first, the signal seemed like an irritating problem. They checked the equipment. They cleaned out pigeon droppings from the antenna, which is a wonderfully unglamorous detail in one of the most important discoveries in cosmology. But the signal remained. It was coming from all directions. Around the same time, theorists had been expecting that an early hot universe should leave behind a cooled remnant glow. The signal Penzias and Wilson found matched that prediction. The cosmic microwave background became powerful evidence that the universe had once been much hotter, denser, and more compressed than it is today. Later missions measured this ancient light in far greater detail. COBE, the cosmic background explorer, showed that the cosmic microwave background has an almost perfect blackbody spectrum and detected tiny temperature variations across the sky. WMAP, the Wilkinson Microwave Anisotropy Probe, mapped those variations more precisely. The Planck spacecraft, operated by the European Space Agency, produced an even sharper map, helping refine measurements of the universe's age, composition, expansion history and early structure. Those tiny temperature variations are not random decoration, they are clues. They show where the early universe was slightly hotter or cooler, slightly denser or thinner. The differences are very small, but they're deeply important. They're connected to the seeds of galaxies and galaxy clusters. In a sense, the cosmic microwave background is a baby picture of the universe, though one where the baby is everything, everywhere, and already more than 300,000 years old. This pushes the idea of old light almost as far as direct light can take us. Galaxies can be seen billions of years in the past, but the cosmic microwave background reaches back further, to a time before galaxies existed at all. It is not a picture of stars or worlds. It is a picture of the universe becoming transparent. So when astronomers study this faint microwave glow, they are not only looking across space, they are reading the oldest visible message the universe has sent. It has travelled since the early cosmos first allowed light to move freely, stretched by expansion, cooled by time and preserved across the sky. Beyond ancient galaxies lies this quiet afterglow. The oldest light we can see is not bright like a star, or dramatic like a supernova, or shaped like a galaxy. It is faint, smooth, nearly uniform and everywhere. A soft relic of the young universe, still arriving after almost all of cosmic history has passed. It is natural to imagine that somewhere, spread across the entire universe, there is one perfect moment called now. On Earth, this idea feels obvious. A clock ticks on the wall. A person walks down a street. A star shines overhead. Somewhere else, a wave reaches a shore, a satellite crosses the sky, and a distant planet turns quietly in the dark. It seems reasonable to think that all these things are happening together, inside one shared present that stretches from here to the edge of everything. But modern physics does not describe time in quite that simple way. Special relativity changed the old idea of a single universal now. Published by Albert Einstein in 1905, special relativity began with two central principles. The first is that the laws of physics are the same for observers moving at constant velocity relative to one another. The second is that the speed of light in vacuum is the same for all such observers, no matter how they're moving. Those ideas sound calm enough at first, almost modest, but once followed carefully, they reshape the meaning of time, distance, and simultaneity. Simultaneity means events happening at the same time. In everyday life, this seems straightforward. If two lights flash at opposite ends of a room, and the flashes reach someone standing in the middle together, it is easy to say the flashes happened at the same time. But relativity asks what happens when observers are moving relative to one another, especially across large distances. The answer is stranger than ordinary intuition expects. Imagine two lightning strikes hitting far apart along a railway track. A person standing halfway between them may see both flashes arrive at the same moment and conclude that the strikes happened simultaneously. But a person on a fast-moving train passing through that midpoint may be moving toward one flash and away from the other. Because light travels at the same speed for both observers, the moving observer may receive one flash before the other, and may calculate that the strikes did not happen at the same time. This is not because one observer is foolish, or because lightning is trying to be difficult, although lightning does have a naturally dramatic personality. The difference comes from the structure of space and time. In special relativity, two observers moving differently can disagree about whether distant events are simultaneous, and both can be correct within their own reference frame. A reference frame is a way of describing measurements from a particular state of motion. This does not mean reality is random. It does not mean anything goes. Relativity is not saying that time is whatever someone feels like after a confusing afternoon. It is a precise physical theory with strict rules. Observers may disagree about timing, distances, and simultaneity, but their measurements are related by consistent mathematical transformations. The universe is not loose or careless. It is structured more subtly than common sense first suggests. One way to make the idea gentler is to think about separated clocks. If two clocks are near each other, comparing them is simple. Bring them side by side, watch them tick and check whether they agree. But if clocks are very far apart, deciding whether they show the same time depends on how signals travel between them. Since light and other signals take time to cross distance, synchronizing distant clocks is not as simple as glancing from one to the other. The very act of defining at the same time across distance depends on assumptions about light signals, motion, and reference frames. This is where the idea of one universal present begins to dissolve. There is no single cosmic clock quietly ticking the same now for every observer in every galaxy. The universe does not hand out a perfectly shared timestamp to everything at once. Instead, time is woven together with space, and measurements of time depend on motion. Hermann Minkowski, one of Einstein's former mathematics teachers, helped give this idea its deeper geometric form. In 1908, Minkowski presented the concept of space-time, showing that space and time should not be treated as entirely separate backgrounds. Events do not simply happen in space while time flows independently above them. They happen in space-time, a combined structure in which where and when are linked. Space-time does not erase the difference between space and time. A meter is not the same thing as a second, and a bedroom is not a Tuesday, no matter how sleepy Tuesday may feel. But space-time shows that space and time are connected in a way that becomes unavoidable when motion approaches the speed of light or when very distant events are compared. What one observer separates neatly into space and time, another observer in motion may divide differently. This is a deeper shift than the delay of old light. The cosmic microwave background showed that light from the young universe can still reach us after travelling for almost all of cosmic history. Ancient galaxies showed that looking outward means looking backward. But special relativity adds something even more unsettling and elegant. It is not only that distant things are seen late, it is that the idea of what is happening right now in distant places is not universal in the old Newtonian sense. There is still a local present. There is still the moment of experience, the clock on the wall, the breath in the body, the light entering the eye. Nearby, at ordinary speeds, time behaves so closely to common sense that life moves along without needing relativity for every cup of tea. But across great distances, and for observers moving differently, the universe no longer supports one obvious present shared by all. The world you see is already in the past because light takes time to arrive, but the wider universe is stranger still. The present itself is local, shaped by motion, distance, and the finite speed of signals. Time is not a single silent river flowing evenly through all places. It is part of the fabric of space-time, and every observer travels through that fabric along their own path. Moving clocks do not always agree. That sounds wrong at first, because clocks are supposed to be the sensible objects in the room. They tick, they count, they sit on walls and wrists and phone screens with a kind of quiet confidence. A clock seems like the thing you bring into a confusing situation when you want less confusion, not more. But in special relativity, time is not a single universal background that all clocks share in exactly the same way. Time depends on motion. This effect is called time dilation. Time dilation means that a moving clock can tick differently when compared with a clock at rest relative to an observer. More specifically, if one clock moves very quickly relative to another, the moving clock is measured to tick more slowly. This does not happen because the moving clock is broken. It does not happen because the observer is fooled by appearance. It is not a trick of perspective, like a distant person looking smaller, or a train seeming to shrink into the horizon. Time dilation is a real, measurable physical effect. At ordinary speeds, the effect is incredibly small. Walking across a room, riding in a car, or flying in a passenger aircraft does not make time behave in a way the body can notice. Life continues as expected. Tea cools at a reasonable speed. Toast still manages to burn when ignored for only a suspiciously brief time. The difference is far too tiny to matter in everyday experience. But when speeds become a significant fraction of the speed of light, time dilation becomes much stronger. This follows from the same ideas that change simultaneity. In special relativity, the laws of physics are the same for observers moving at constant velocity, and the speed of light in vacuum is the same for all such observers. Those principles force space and time to adjust together. If every observer measures light in vacuum as travelling at the same speed, then measurements of distance and time cannot remain absolute in the old familiar way. Something has to give, and what gives is the simple Newtonian picture of one shared time ticking identically everywhere. A fast spacecraft is an easy way to picture it. Imagine a spacecraft travelling close to the speed of light, while a clock remains on Earth. From the viewpoint of people on Earth, the spacecraft's clock would tick more slowly than the Earth clock. If the spacecraft travelled out and returned, less time could pass for the travellers than for people who remained behind. This idea is often called the twin paradox, though the word paradox is a little dramatic. It is not a contradiction inside relativity. It only feels strange because human intuition was trained at walking speed, not near light speed. Particle physics gives real examples of time dilation. Muons are unstable particles produced when cosmic rays strike atoms high in Earth's atmosphere. Muons decay very quickly, so if time behaved in the old simple way, many of them should not survive long enough to reach the ground. Yet detectors at Earth's surface do observe them. One reason is time dilation. From our viewpoint, the fast-moving muons experience time differently, allowing more of them to reach the surface before decaying. The particles are not being sentimental about visiting Earth. They are obeying relativity. Particle accelerators also confirm this effect. In machines where particles are pushed to extremely high speeds, their lifetimes and behavior match the predictions of special relativity. Scientists do not treat time dilation as a philosophical curiosity. They have to account for it in real measurements. It is built into the working language of high-energy physics. Time dilation has also been tested with clocks directly. In the Huffle-Keating experiment in 1971, physicists Joseph Heifel and Richard Keating flew atomic clocks around the world on commercial aircraft and compared them with atomic clocks left on the ground. The airborne clocks showed tiny differences, consistent with the combined effects of special relativity and general relativity. The differences were extremely small, measured in billionths of a second, but atomic clocks are precise enough to reveal them. Time did not simply tick identically for all clocks. Motion and gravity mattered. This is one of the important clarifications. Time dilation is not just about how things look from far away. Light travel delay can affect what an observer sees, because light takes time to arrive. But time dilation is deeper than appearance. It is about how much time actually passes along different paths through space-time. A moving clock is not merely seen to run differently because its image arrives late. When the clocks are brought back together and compared, their readings can genuinely differ. This connects directly to the idea that the world you see is already in the past. At first, the delay seemed simple. Light travels, the eye receives it, and the brain processes it. The moon appears just over 1 second old. The sun appears more than 8 minutes old. Stars and galaxies appear older still. But relativity shows that delay exists inside an even stranger structure. It is not only that signals travel through time, it is that time itself is not absolute for all observers. The previous idea, the relativity of simultaneity, showed that observers moving differently can disagree about whether distant events happen at the same time. Time dilation adds another piece. Observers can also disagree about how much time passes between events, depending on their motion. Both ideas weaken the old picture of a single universal present, ticking everywhere with perfect fairness and no local complications. The universe is not unfair exactly. It is just more precise than human expectation. Each object follows its own path through space-time. Along that path, time accumulates in a way that depends on motion and gravity. A clock on Earth, a clock in a spacecraft, a muon racing through the atmosphere, and a particle circling inside an accelerator do not all share one simple cosmic ticking. So the visible world arrives late because signals take time to reach you. But the larger lesson is quieter and deeper. There is no single master clock behind the universe, handing every observer the same now. Moving clocks reveal that time is flexible, measured, and physical. The past you see arrives through light, but the meaning of past and present belongs to a universe where time itself bends with motion. Gravity does not only shape the paths of planets, moons, falling stones, and drifting dust. It also shapes time. That idea feels less familiar than motion changing time, because gravity is often imagined as a pull. In everyday life, gravity is the reason things fall, the reason feet stay on the ground, the reason oceans cling to Earth, and the reason putting something on the edge of a table remains a daring experiment in regret. But in modern physics, gravity is not described only as an invisible tug between masses. In general relativity, gravity is understood as the curvature of space-time. Albert Einstein published general relativity in 1915, 10 years after special relativity. Special relativity showed that motion changes measurements of space and time. General relativity went further. It described gravity as the way mass and energy curve space-time, and the way objects move through that curved space-time. Earth orbits the Sun, not because it is being pulled through ordinary flat space in the old simple sense, but because the Sun's mass curves space-time around it, and Earth follows a path through that curvature. This means time is part of the gravitational story. The effect is called gravitational time dilation. A clock deeper in a gravitational field ticks more slowly when compared with a clock farther away from that gravitational field. In simpler terms, time passes very slightly more slowly closer to a massive object. A clock near Earth's surface ticks a little more slowly than a clock high above Earth, because the clock on the surface is deeper in Earth's gravity. The difference is tiny in daily life. If one clock is at sea level and another is on a mountain, they will not drift apart in any way a person can feel. Nobody climbs a hill and returns mysteriously younger in a way that causes awkward passport questions. But with precise atomic clocks, the effect can be measured. Time is not flowing at exactly the same rate everywhere around Earth. It changes slightly with altitude. This is not because clocks are badly made. It is not because gravity physically jams the gears or makes the ticking mechanism tired. The effect applies to time itself, as measured along different paths through space-time. Whether the clock is mechanical, atomic, biological, or based on any other regular process, gravitational time dilation reflects a real difference in how time passes. One important confirmation came from the Pound-Rebka experiment in 1959. Robert Pound and Glenn Rebka tested a prediction of general relativity using gamma rays inside a tower at Harvard University. They measured how light changed as it moved through Earth's gravitational field. Their results supported the idea of gravitational redshift, which is closely linked to gravitational time dilation. Light climbing away from a gravitational field loses energy and shifts toward longer wavelengths. This was not just a beautiful idea on paper, it was a measurable effect. Modern atomic clocks have made the evidence even clearer. Atomic clocks are so precise that scientists can detect differences in time between clocks placed at different heights. Even a relatively small change in altitude can produce a measurable difference if the clocks are accurate enough. Time, in this very gentle earthly example, becomes something with a vertical gradient. Higher clocks tick slightly faster than lower ones. Earth gives only a mild version of the effect because Earth's gravity, while strong enough to keep oceans, mountains, and people attached to the planet, is not extreme by cosmic standards. Around much denser objects, gravitational time dilation becomes far more dramatic. A neutron star, for example, packs more mass than the Sun into a sphere only about the size of a city. Its gravity is so intense that time near its surface would pass noticeably differently compared with time far away. Black holes carry the idea even further. A black hole is a region where gravity is so strong that, beyond the event horizon, light cannot escape to distant space. Near a black hole, space-time curvature becomes extreme, and gravitational time dilation can become enormous. To a distant observer, processes near the event horizon can appear slowed and redshifted. Light escaping from near the black hole loses energy as it climbs outward, and the timing of events becomes deeply shaped by gravity. This does not mean time simply stops for someone falling through the event horizon of a large black hole. For the falling observer, their own clock keeps ticking normally along their path. The strangeness appears when comparing that clock with faraway clocks, or when asking how signals from near the black hole reach distant observers. General relativity is careful about viewpoint. The answer depends on the path, the observer, and the geometry of space-time. This builds naturally from moving clocks. Special relativity showed that motion changes time. General relativity shows that gravity changes time as well. The old idea of one universal clock becomes even harder to keep. Time is not a single invisible river flowing evenly everywhere. It is physical, local, and connected to the shape of space-time. So when you look at the world and see the past arriving through light, that delay belongs to a universe where time itself is not simple. Signals take time to travel. Moving observers measure time differently. Clocks deeper in gravity tick at different rates from clocks higher up. Every now is tied to location, motion, and gravitational environment. The present is not floating above physics, it is part of physics. The global positioning system works because time is measured with extraordinary precision. It may feel in daily life as if satellite navigation is mostly about maps. A phone opens, a little dot appears, and after a short moment of uncertainty, it tells you where you are. Sometimes it does this beautifully. Sometimes it places you in the middle of a nearby building, a river, or a field you have never visited, just to keep humility alive. But beneath the map, beneath the route, beneath the calm little arrow telling you to turn left, there is a deeper physical trick taking place. Satellite navigation is built on timing. The Global Positioning System, often called GPS, is a network of satellites that send signals down to receivers on Earth. A receiver might be inside a phone, a car, an aircraft, a ship, or a specialized scientific instrument. Each satellite broadcasts information, including the time the signal was sent and the satellite's position. The receiver compares signals from several satellites and calculates how long each signal took to arrive. Since radio signals travel at the speed of light in vacuum, and slightly differently through Earth's atmosphere, that travel time can be converted into distance. In simple terms, the receiver works out how far away it is from multiple satellites. With enough satellites, it can determine its position on Earth. This process is called trilateration. It is not based on asking one satellite, "Where am I?" and receiving a helpful answer. It is based on timing several delayed messages and using those delays to calculate location. That means tiny errors in time can become large errors in position. Light and radio waves travel incredibly fast, about 300,000 kilometers per second in vacuum. So if a timing measurement is wrong by even a tiny fraction of a second, the distance calculation can be wrong by many meters, or even much more. A navigation system that cannot measure time accurately cannot locate you accurately. It might know you're somewhere on Earth, which is nice, but not exactly enough when trying to find a hospital, an airport gate, a walking route, or the car that somehow vanished in a large car park while you're absolutely certain you parked near the blue sign. This is why GPS satellites carry atomic clocks. Atomic clocks use the regular behavior of atoms to keep time with extraordinary precision. Their accuracy makes satellite navigation possible because the system depends on comparing signal travel times extremely carefully. The clocks in the satellites and the calculations performed by receivers must be coordinated with great precision. But there is a complication. Time is not simple. The satellite clocks do not tick at exactly the same rate as clocks on Earth. Two effects from relativity matter at the same time. Special relativity matters because the satellites are moving quickly as they orbit Earth. A moving clock, compared with a clock on the ground, is affected by time dilation. From the viewpoint of clocks on Earth, the motion of the satellite tends to make the satellite clock tick slightly more slowly. General relativity also matters because the satellites are much higher above Earth's surface. They are farther from Earth's gravitational field than clocks on the ground. A clock higher up, in weaker gravity, ticks slightly faster than a clock deeper in Earth's gravity. For GPS satellites, the gravitational effect is larger than the motion effect. So overall, the satellite clocks would tick faster than ground-based clocks if corrections were not applied. The differences are small, but they are not optional. If relativity were ignored, the positioning errors would grow quickly. Over the course of a day, the system could drift by kilometers. In other words, Einstein's theories are not only useful for black holes, particle accelerators, and thoughtful documentaries about time. They help keep your map from confidently guiding you into a pond. The Global Positioning System is operated by the United States Space Force, and it depends on satellites, ground control stations, atomic clocks, orbital calculations, and careful correction of signal delays. The system also has to account for effects from Earth's atmosphere, because signals can be delayed as they pass through the ionosphere and the troposphere. Navigation is not just a matter of satellites shouting from space. It is a carefully managed conversation between clocks, signals, orbits, and physics. Other satellite navigation systems work with the same broad principles. Galileo is operated by the European Union. GLONASS is operated by Russia. Beidou is operated by China. These systems also depend on precise timing, satellite signals, orbital knowledge, and relativistic corrections. They're different systems with different histories and designs, but they all live inside the same universe, where signals take time to travel and clocks do not all tick identically. This connects directly to gravity changing time. A clock on Earth and a clock in orbit do not experience exactly the same conditions. Their motion differs, their gravitational environment differs, their paths through space-time differ. Satellite navigation works only because those differences are measured, predicted, and corrected. The strange ideas of special relativity and general relativity are not distant curiosities. They're quietly built into the technology people use every day. This is one of the most elegant examples of the hidden physics behind ordinary life. A phone finding its location is not simply drawing a dot on a map. It is receiving delayed radio signals from satellites moving high above Earth. It is comparing times. It is using the speed of light. It is relying on atomic clocks. It is correcting for motion and gravity. It is turning relativity into directions. So the world you see is already in the past because signals need time to arrive. But the same principle also helps the modern world navigate. Delayed signals are not merely a limitation, they can become a tool. By measuring how late a message arrives, a receiver can discover where it is. Time is not simple, and because it is not simple, you can find the cafe, the hospital, the airport, or, with enough patience and emotional resilience, the car. Black holes are where delay stops being gentle. Around Earth, relativity is subtle enough to hide inside satellite navigation. The clocks aboard Global Positioning System satellites tick differently from clocks on the ground, and the system works because those differences are carefully corrected. Time changes there, but quietly. It becomes a practical detail, a hidden adjustment helping someone find a road, a hospital, or a suspiciously well-hidden parked car. Near a black hole, the same principles become extreme. A black hole is not simply a very heavy object. It is a region of space-time where gravity has become so intense that beyond a certain boundary, light can no longer escape to distant observers. That boundary is called the event horizon. It is not a solid surface. You could not tap it with a tiny cosmic spoon and hear a satisfying knock. It is a boundary in causality, a line beyond which future paths lead inward rather than back out into the wider universe. The event horizon is central to the question of what can and cannot be seen. Outside it, light can still escape if it moves along the right path. Near it, light can be bent, stretched, delayed, and dragged into complicated routes by the curvature of space-time. Inside it, light cannot escape outward to distant space at all. The event horizon is therefore not just a dramatic phrase, it marks the limit of communication. Events beyond it cannot send light signals back to the outside universe. This is where the idea of seeing the past becomes especially strange. When matter falls toward a black hole, a distant observer does not see it simply drop through in the ordinary way. As the matter approaches the event horizon, the light coming from it has to climb out of an increasingly intense gravitational field. That light loses energy as it escapes, stretching toward longer wavelengths. This effect is called gravitational redshift. At the same time, signals from the falling matter appear increasingly delayed to a distant observer. Each new signal has more difficulty escaping from closer to the event horizon. The image can seem to slow, dim, and redden. From far away, the falling object appears to approach the horizon more and more slowly, its light becoming fainter and more stretched. But it is important not to turn this into the misleading idea that the falling object literally freezes for itself at the horizon. From the object's own viewpoint, if it could survive the journey, it would cross the event horizon in a finite amount of its own time. Its own clock would continue ticking normally along its path. The freezing is not what the falling traveller experiences, it is how the signals reaching a distant observer behave. Black holes are very good at forcing physics to ask, from whose point of view, which is inconvenient, but also rather elegant. The mathematics behind black holes came from general relativity. Soon after Einstein published the theory in 1915, Carl Schwarzschild found a solution to Einstein's field equations, describing the space-time around a spherical non-rotating mass. This Schwarzschild solution revealed the possibility of a radius now associated with the event horizon. At the time, black holes were not yet understood as physical astrophysical objects in the modern sense, but the theory already contained the seed of the idea. Today, black holes are supported by many kinds of evidence. Astronomers observe stars orbiting unseen compact masses, hot gas spiraling into dark centers, X-rays from accretion disks, gravitational waves from black hole mergers, and light bent by strong gravity. Black holes are no longer just mathematical curiosities. They are real objects in the universe, and some of them sit at the centers of galaxies. One of the most important modern achievements came from the Event Horizon Telescope collaboration. The Event Horizon Telescope is not one single telescope, but a network of radio observatories around Earth, working together through a technique called very long baseline interferometry. By combining data from widely separated telescopes, scientists can create an Earth-sized observing instrument in effect, giving enough resolving power to study the regions around supermassive black holes. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, showing the supermassive black hole at the center of the galaxy Messier 87. The image did not show the event horizon directly as a surface. Instead, it showed glowing material around a dark central shadow shaped by extreme gravity. The light in that image had travelled about 55 million years before reaching Earth. It was a picture of an extreme gravitational environment, but also a message from deep time. Later, the collaboration released an image of Sagittarius A star, the supermassive black hole at the centre of the Milky Way. That light had travelled for about 27,000 years before reaching us. Compared with Messier 87, Sagittarius A star is practically local by cosmic standards, but still far beyond everyday distance. The image revealed the nearest supermassive black hole not as it is this instant, but as its delayed light allowed it to be seen. Black holes therefore combine several themes at once. Light takes time to arrive. Gravity changes time. Strong gravity redshifts escaping light. The event horizon limits what can ever be communicated outward. Observations depend on signals that have travelled across space, sometimes for thousands or millions of years before they can be studied. Around Earth, relativity quietly corrects satellite clocks so navigation can work. Around black holes, relativity becomes the whole landscape. Time, light, gravity, and visibility are no longer background details. They are the story itself. A black hole marks the edge of delay in one of the deepest senses. Not because everything outside it stops, and not because time becomes a simple frozen picture, but because the flow of information is bent to its most extreme visible limit. Light struggles outward, signals stretch, clocks disagree, and beyond the event horizon, the universe stops sending messages back. Visible light is only one way the universe sends its path to us. For most of human history, astronomy was almost entirely the study of light that human eyes could see. Stars, planets, comets, eclipses, and the pale band of the Milky Way all arrive through visible light. Telescopes extended that sight, gathering more of the same kind of glow. But the universe is not limited to the colours the eye can notice. It sends messages in many forms, and modern astronomy listens across a much wider range. Radio waves, infrared light, ultraviolet light, X-rays, and gamma rays are all part of the electromagnetic spectrum. They are related to visible light, but they have different wavelengths and energies. Radio waves can reveal cold gas, pulsars, and jets from active galaxies. Infrared light can pass through dust and show warm objects hidden from ordinary vision. X-rays can reveal hot gas around black holes, neutron stars, and galaxy clusters. Gamma rays can come from some of the most energetic events known, including violent explosions and extreme particle interactions. All of these are still light in the broader scientific sense. They are forms of electromagnetic radiation. They travel through vacuum at the same fundamental speed, and they carry information from events that have already happened. A radio signal from a distant galaxy, an infrared glow from a forming star, or an X-ray flare near a black hole is not arriving from the exact present. It is a messenger from the past, stretched across distance. But astronomy now goes even further than electromagnetic radiation. It also studies particles and ripples in space-time itself. This wider approach is called multi-messenger astronomy. The idea is simple and powerful. Different kinds of cosmic messengers can reveal different parts of the same event. Instead of relying only on light, scientists can combine light with neutrinos, cosmic rays, and gravitational waves, building a richer picture of violent and distant processes. Neutrinos are tiny, extremely light particles that interact only very weakly with matter. They can pass through planets, stars, and human bodies, almost as if nothing is there. Every second, huge numbers of neutrinos pass through you, which sounds alarming until you remember they are famously antisocial and almost never stop to interact. Because neutrinos can escape from dense environments that trap light, they can carry information from deep inside stars and explosions. One of the most important examples came from supernova 1987A. This supernova happened in the Large Magellanic Cloud, a small neighbouring galaxy of the Milky Way. The light from the explosion reached Earth in 1987, after travelling for about 168,000 years. But before the visible light was widely observed, detectors on Earth recorded a small burst of neutrinos. Those neutrinos had escaped from the collapsing core of the dying star, carrying direct evidence from the heart of the explosion. That was a remarkable moment. A stellar death had not only been seen in light, it had been detected through particles that had crossed intergalactic space. The event itself had happened long before human civilization, but its messengers arrived during the late 20th century, giving scientists a rare chance to compare theory with observation. Supernova 1987. A remains one of the most important events in modern astrophysics because it linked visible astronomy with neutrino astronomy in a deeply concrete way. Gravitational waves opened another kind of listening. These are ripples in space-time produced by accelerating massive objects, especially extreme events such as merging black holes or neutron stars. General relativity predicted gravitational waves, but detecting them required extraordinary precision. The Laser Interferometer, gravitational wave observatory, known as LIGO, made the first direct detection in 2015. The signal came from two black holes merging more than 1 billion years ago, sending a ripple through space-time that eventually passed through Earth. That detection confirmed a major prediction of general relativity and opened a new observational window on the universe. It also proved that even space-time itself can carry old news. The black holes had already merged long before the signal arrived. The event was over, but the gravitational wave continued travelling outward at the speed of light, crossing the universe until instruments on Earth finally measured an incredibly tiny stretching and squeezing of space. Cosmic rays add another messenger, though they are more difficult to trace. They are high-energy particles, mostly protons and atomic nuclei that arrive from space. Some are produced by the Sun, while others come from far more energetic sources beyond the solar system. Because charged particles are deflected by magnetic fields, tracing them back to their origins can be difficult. They still carry evidence of powerful cosmic accelerators, but their paths through space are less straightforward than a beam of light. Each messenger has strengths and limits. Visible light can show stars and galaxies. Infrared light can reveal hidden warmth. Radio waves can map cold hydrogen and magnetic structures. X-rays and gamma rays can expose extreme energy. Neutrinos can escape dense stellar interiors. Gravitational waves can reveal mergers of compact objects even when little or no light is visible. Together, they let scientists study the universe in several languages at once. But none of them remove delay. They all obey travel time. They all arrive after crossing distance. They all tell us about events that have already happened by the time the message reaches Earth. Black holes showed that gravity can bend light, stretch signals, and limit what can ever escape. Multi-messenger astronomy widens the view. Even the most violent events in the universe are known only through the signals they send outward. Light, particles, and ripples in space-time. The cosmos does not hand over its present directly. It sends messages, and every message takes time. The present feels like a single thing. It seems to surround you all at once. The room, the air, the light, the sounds, the weight of the body, the movement of thoughts. Everything appears to be happening together inside one shared moment. And for ordinary life, that feeling is useful. It is how the brain keeps the world manageable. It lets you walk through a doorway, pour a drink, catch a falling object, follow a voice, and avoid stepping on the one creaky floorboard that somehow sounds personally offended. But physics gives the present a quieter and more local meaning. The present is not one perfect cosmic instant delivered everywhere at once. It is better understood as a local experience, built from the information that has reached a particular observer. That information has travelled. It may have crossed a room, or the distance from the moon, or the gulf between galaxies. It may have arrived as light, sound, radio waves, neutrinos, gravitational waves, or pressure against the skin. Whatever form it takes, it is not the universe handing over itself instantly. It is a message arriving after a journey. Nearby, this is almost invisible. Light crossing a room takes such a tiny fraction of a second that it feels immediate. The eye and brain add their own processing time, but the nervous system is very good at smoothing that delay into a stable experience. The retina converts light into electrical signals. The optic nerve carries those signals onward. The thalamus and lateral geniculate nucleus help relay and organize them. The visual cortex builds edges, motion, color, and shape into a world that feels present. The brain does not show you a raw stream of late signals. It gives you a working now. The working now is extraordinarily useful. It is also slightly delayed. The delay grows as distance grows. The moon is seen as it was just over 1 second ago. The sun is seen as it was about 8 minutes and 20 seconds ago. Mars can be seen minutes in the past, with the exact delay changing as Earth and Mars move around the sun. Spacecraft signals from other planets arrive after measurable pauses, forcing mission teams to plan rather than steer distant machines in real time. The solar system is not one instant room. It is a moving arrangement of delayed conversations. Beyond the solar system, delay becomes history. Stars are seen through light that has travelled for years, decades, centuries, or thousands of years. A light year is a distance, not a time, but it tells us how long light has spent crossing space. Proxima Centauri is seen more than 4 years in the past. Sirius is seen more than 8 years in the past. More distant stars arrive from deeper slices of time, scattered across the same night sky. Galaxies take the idea further still. Andromeda is seen roughly 2.5 million years in the past. Deep field images from the Hubble Space Telescope and infrared observations from the James Webb Space Telescope reveal galaxies as they were billions of years ago. The cosmic microwave background reaches even farther back, arriving from the time when the young universe became transparent, about 380,000 years after the beginning of cosmic expansion. The sky is not a single photograph of now. It is a layered archive of arrivals. Relativity deepens the point. Special relativity shows that observers moving differently can disagree about whether distant events are simultaneous. General relativity shows that gravity changes time too. Clocks deeper in a gravitational field tick differently from clocks farther away. Moving clocks and clocks in different gravitational environments do not all share one simple universal rhythm. Time is not separate from physics. It is part of space-time, shaped by motion and gravity. Causality depends on this structure. An event can only affect another event if some signal, influence, or physical connection can travel between them. Since usable information cannot travel faster than light and vacuum, distant events cannot affect you until their messages have had time to arrive. This is not merely a delay in awareness. It is a rule about what can be connected to what. In relativity, one useful way to picture this is with light cones. A light cone is a conceptual boundary around an event showing what that event can influence and what can influence it, limited by the speed of light. Events inside the future light cone can, in principle, be affected by the original event. Events inside the past light cone can, in principle, have affected it. Events outside those boundaries are too far away in space and time for a signal moving at light speed or slower to connect them yet. The idea sounds abstract, but the meaning is simple. The universe has rules about which moments can talk to each other. This is why the present is local. It belongs to an observer's position, motion, gravitational environment, and received information. Your now is not false. It is not an illusion in the sense of being meaningless. It is the real local present of your experience, built from the signals available to you. But it is not the same as one universal now spread cleanly across the cosmos. Everyday life remains stable because the nearby delays are tiny and the brain handles them beautifully. The cup is where you reach for it. The voice belongs to the person speaking. The floor stays put, which is always thoughtful of it. For human scales, the local present works well enough that it feels immediate. But beneath that smoothness, the deeper truth remains. The world seen by any observer is always an arrival. Sometimes it is the very recent past, carried across a room and shaped by the brain. Sometimes it is ancient starlight. Sometimes it is a galaxy from billions of years ago. The present is not delivered whole from everywhere at once. It is assembled locally, from messages that have already travelled through space and time. So why is the world you see already in the past? Because nothing reaches awareness without first making a journey. Light has to travel. Sound has to travel. Gravitational changes have to travel. Radio waves, X-rays, neutrinos, gravitational waves, and every physical signal that carries information must cross the distance between an event and an observer. And once those signals arrive, the body still has to receive them, translate them, and shape them into experience. The present, as it appears in awareness, is not handed over instantly. It is built from arrivals. The delay begins in the most ordinary places. A lamp across the room seems to brighten the eye immediately, but its light still has to cross the space between the bulb and the retina. A face across a table seems perfectly present, but what reaches you is reflected light from skin, eyes, hair, and expression. A book on a shelf, dust in a sunbeam, a glowing screen, a cup resting quietly beside you, all of them are seen because light has travelled from them into the eye. Then the eye begins its own work. The cornea and lens focus incoming light. The retina receives it. Rods and cones respond. Phototransduction turns light into electrical signals. The optic nerve carries those signals toward the brain. The thalamus, the lateral geniculate nucleus, and the visual cortex help organize the message into edges, motion, color, depth, and meaning. Seeing is not simply contact with the world. It is physics meeting biology. and biology turning late information into a useful now. Sound makes the delay easier to notice. Lightning flashes before thunder rolls because light crosses the distance far faster than sound does through air. Distant fireworks bloom before their booms arrive. Echoes return after sound has travelled outward, reflected, and come back. Sound reveals in a more obvious way what light often hides. Events do not arrive all at once. The senses receive different messengers at different speeds, and the brain binds them together into one calm experience. Reflections quietly say the same thing. A mirror does not show a magical present. It returns light. Light leaves an object, strikes the mirror, reflects according to the law of reflection, and travels into the eyes. Still water, polished metal, glass at night, and moonlight shimmering across the ocean all depend on paths of reflected light. Every reflection is a small echo made of brightness, a returned past with a polished surface. The moon makes the delay large enough to name. Its light takes just over 1 second to reach Earth after reflecting from the lunar surface. The moon is not shining with its own light, but scattering sunlight from dust, rock, craters, and ancient plains. Lunar laser ranging using retroreflectors placed during the Apollo program shows how light travel time can measure distance with extraordinary precision. A pulse of light can leave Earth, touch a device on another world, and return with a measurement. The sun stretches the delay further. Sunlight takes roughly 8 minutes and 20 seconds to reach Earth across about 150 million kilometers. The sun seen in the sky is therefore not the sun at this exact instant. Its light comes from the photosphere after energy has worked outward from nuclear fusion in the solar core, through hot plasma and complex layers of scattering. Daylight feels immediate because life on Earth has always lived inside that delay, but it is still delayed. Morning is the sun arriving late, beautifully and right on time. The planets show that delay is not fixed. Mars may be seen only a few minutes in the past when it is relatively close, or more than 20 minutes in the past when it is farther away. Spacecraft signals take time to cross the solar system, which is why Mars rovers cannot be driven like remote control cars. NASA, the Jet Propulsion Laboratory, and mission teams must plan around signal delay, turning distance into careful patience. Stars carry the idea into years. A light year is a distance, not a time, though the name does enjoy causing trouble. Proxima Centauri is seen more than 4 years in the past. Sirius is seen more than 8 years in the past. Many stars in the night sky shine from decades, centuries, or thousands of years ago. Stellar Parallax, Friedrich Bessel's work, and the European Space Agency's Gaia mission all help measure those immense distances, turning the sky into a map of delayed messages. Telescopes deepen the view. Galileo Galilei's early observations in 1610 began a new age of looking, but modern observatories such as the Hubble Space Telescope and the James Webb Space Telescope reveal not only distant objects, but old light from earlier ages of the universe. Galaxies become fossils made of light. Andromeda appears roughly 2.5 million years in the past. Deep field images show galaxies from billions of years ago. Beyond them lies the cosmic microwave background, the oldest light directly observed, released when the universe became transparent about 380,000 years after the beginning of cosmic expansion. Relativity changes the meaning of the present even more deeply. Albert Einstein's special relativity showed that observers moving differently can disagree about whether distant events are simultaneous. Moving clocks tick differently when compared with clocks at rest relative to an observer. General relativity showed that gravity changes time too, with clocks deeper in a gravitational field ticking more slowly than clocks farther away. Satellite navigation works because systems such as the Global Positioning System correct for these effects. Black holes reveal them in extreme form, where light is redshifted, signals are delayed, and beyond the event horizon, messages cannot return. And still, the universe sends other messengers: radio waves, infrared light, X-rays, gamma rays, neutrinos, cosmic rays, and gravitational waves. Multi-messenger astronomy shows that even the most violent cosmic events are known only through signals that have already crossed space. LIGO detected gravitational waves from black holes that merged long before the ripple reached Earth. Neutrinos from supernova 1987A arrived from a stellar explosion in the Large Magellanic Cloud after travelling for about 168,000 years. None of this makes reality fake. It does not make the world unreachable. It simply means awareness is always built from information that has travelled. Nearby, the delays are so tiny that life feels immediate. Far away, the same principle becomes breathtaking. There is no single universal now delivered everywhere at once. Every observer receives a local present, shaped by distance, motion, gravity, signal travel, and the quiet labour of the brain. To look around is never quite to touch the instant itself. It is to receive the universe a little late, from the glow of a nearby lamp to the oldest light still travelling through the dark.